So first let me thank Earl and Hyperion for having us and to place us in a subtopic called the Leadership Computing Initiative. So it certainly is an initiative, and I want to thank Irene for expanding that definition to include things beyond exascale. This is certainly beyond exascale. Our marketing department has captured the essence of this project in a short minute-and-a-half video. So let me see if I can get that going.
Humans have long wondered about Mars. What's it like? Does it have life? When will we be able to get there to find out? To get there, humans need to conquer space and time. The distance is so vast that a radio signal hurtling at the speed of light would take up to 20 minutes to travel from the desolate red planet to Earth, and another 20 minutes to travel back. So, if an astronaut has a problem, mission planners wouldn't be able to transmit a solution back to Mars for more than half an hour. What NASA needs is a nearly magical machine to travel along with the space voyagers, a system that can crunch data in real time and provide insights on the spot. And that machine has to be lightweight, energy efficient, and be able to survive the otherworldly rigors of space travel. That's where Hewlett-Packard Enterprise comes in. HPE is partnering with NASA to literally conquer space and time by sending its Apollo Spaceborne Computer aboard the Dragon spacecraft to the International Space Station. It will circle the Earth thousands of times, journey millions of miles, and compute data in the harsh conditions of space for a year, roughly the same amount of time it will take on a 130 million mile journey. HPE's innovation is helping us get one step closer to Mars.
Okay. So the first part of this presentation is going to be quick. It's going to be lighthearted. It's things that over the past year people have found fascinating to see that they weren't familiar with and how we got there. So let me begin by just going over our mission or science objectives. The top 3 bullets there are the official ones that are in paperwork. Very quickly, we wanted to know, can we package a pizza box server for space flight? Will it survive the G-forces, which can range from -2 to +6? Can it survive storage in the coldness of space? Can we get astronauts who are not IT experts to install it? If it is powered up, will it operate correctly? Will it give me the right answers? And what sort of data center support issues may I have? And will it continue to give me the right answers? Our team is shown here. It's a team of 7. It's a very small focus group. I could spend 30 minutes telling you how this team came to be and why each of them is important and why you might need a regulatory engineer or an actual technical writer. But let me move on in the interest of time. Why are we doing this? This is yours truly photographed in front of a mural at NASA Kennedy. Before we go to Mars, we have to know. What do we have to know? On the left, you'll see characterizations of what they call the core computer systems, and they're focused on flight, their propulsion, the guidance, etc. And those are remarkably antique systems. 1 and 2 cores running in the gigahertz range. They've been hardened. I haven't heard of one that is under 10 years old that has made it to flight, and they run a couple $100,000 each. But those are essential. Now, when we move from beyond going somewhere just to say that we've been there, we're going to want to do some science, some research, some engineering. And that's the purpose of Spaceborne Computer. Can you take a off-the-shelf commodity box with you in order to do all that data processing? I've discussed this topic and been fascinated by 4th grade students. They get very excited, great questions. And I've also discussed things with aerospace grad engineers. This statement here generally gets all the jaws to drop and all the eyebrows to rise. And I finish up with saying, in your graduate studies, is there a course where you study heat in zero gravity? It will not move. You have to handle it. One of the patent disclosures that we currently have is how to cool Spaceborne Computer in zero G. Here it is shown in what is called the NASA-approved Express Rack Locker. You can see the two pizza box servers here. We have redundant Ethernet switches. We have a heat exchanger. It is a water-cooled miniature supercomputer aboard the International Space Station. Very quickly, I'm going to skip all the hard work it took to get us to Kennedy Space Center. Everyone, including the fourth graders, knew where Walt Disney World is. That little black notch there is Kennedy Space Center. We were invited as special guests to witness the launch of SpaceX 12. This is my wife. She made that dress. It's got planets and stars and such all over it, and she's very excited to be there. When we arrived at the auditorium, none other than Buzz Aldrin gave us a talk before the launch. That was very exciting. I have to explain to many people who he is. So there's no American flag there. One of the more, yeah, right. There, my wife and I are. In the background, you see pad 39A, which is where Buzz Aldrin departed to land on the moon. We are a little over 2 miles from the launch pad. I'm not going to bore you with how bad I am at taking cell phone videos. SpaceX does a very good job at that, and you can grab those off of YouTube. I want to stop here at T plus 11 seconds and point out two things. Sound travels about 1 mile in 5 seconds. We're a little over 2 miles. So at about the 10-second to 11-second is when the sound and the heat hits you on the observation deck. It has cleared the launch pad by at least one length. Okay? I'm going to attempt to do this and show you something that fascinates both fourth graders and grad students. This is a good cell phone video. You'll hear the countdown, and as soon as we get to T0, there will be applause from everyone standing on that observation deck. About 10 to 11 seconds into that, the applause dies down, and you'll hear someone say, "There she goes," but if you listen, you can hear the roar hit you. So let's see if this will work today. Now let me play that one more time, and this time I'm going to let it continue to run past that point. As the rocket continues to go, your visuals of what you see mentally will link up with what you hear, but that is incorrect. Don't you now think that sound is coming from that rocket and they are linked? They are not. So again, 24 minutes to Mars, 24 minutes back at the speed of light, and this is an example of how, in fact, speed of sound can illustrate that delta. All right, on to some more fun stuff. We launched at 12:31 p.m. That's pretty exciting. If you've never seen a rocket launch, it is pretty cool. The landing of the SpaceX is 10 times cooler. You've got to see that. It occurs about 9 minutes after launch. Okay. So where were we headed? We were headed to the U.S. Destiny module aboard the U.S. International Space Station. We spent a month waiting patiently in the cold darkness of storage aboard the Dragon spacecraft, and then our day came. 1 month later, September 14th, astronaut Mark Vande Hei is preparing to install a Spaceborne computer. He looks like a regular technician in khakis and a polo shirt working at his laptop prior to going to work. We watched this live. And with the flick of a finger, he's suddenly doing his best Spider-Man imitation, hanging on to the ceiling of the space lab. Here on Earth, we laid out computers in racks, but if you have zero gravity, you can also put a rack in the ceiling. Spaceborne Computer is installed in the ceiling. So Mark Van de Hey is inspecting where in the rack he will install Spaceborne Computer. He's got it figured out. He takes a look and says, "Let me go get it." Off he drifts to the Dragon spacecraft to return with Spaceborne Computer. What seems like forever, he returns, and he's carrying the 124-pound Spaceborne Computer effortlessly and moving it into position. Here it is installed, ready to rock and roll. And then from NASA, we get Spaceborne Computer, you're a go for ops. That means that we're ready to start operating. Up until that point, all we're able to see is where the International Space Station was located and the live video feed. Well, remote gets a whole new meaning when you can SSH into the International Space Station. And for those that are looking carefully, we are running LINPACK in the bottom. It's one of the first things we did. Many naysayers did not think the system would last but just a few minutes. So we want to get the LINPACK run in. We did 1.1 thousand gigaflops of the first teraflop on board. The secondly we ran was HPCG, and it made the highlight reel at SC17, and we made the list. We are the 115th fastest submitted HPCG results on Earth or elsewhere. We got an award, the HPC 2017 Top Supercomputing Achievement Award. We got an even better and more important award from Hyperion about innovation. And we've also part of their reports as well. Most recently, we've got an award from the ISS R&D conference on not only development, but deployment of a technology. So they're very careful to split those apart. By this time, astronaut Mark Van de Hey and his assistant Randy Bresnik had made it back to Earth. That's me pictured with them in their spacesuits, in their flight suits, giving us an award. And for those that know John Kachuri, there's a picture of him also with Mark Van de Hey. This is the only HPE-approved picture of Spaceborne Computer for use in public. And I can tell you it was weeks of photoshopping to get it approved, beyond my recognition of what all they have to do. This is Earthborne Computer. We run a parallel system on Earth to compare results to, and it's what you would expect in a lab. There's a power strip hanging off of it, some laptops laying around, wires everywhere. That's what it looks like. But as you know, when we deploy something into production, it's in a really cool-looking place, and the public can see it, and everything's nice and clean and sweet. Here's our production version. I think the ISS was deployed prior to us inventing cable management. All right, so we've had some fun along the way. Each day we woke up expecting the naysayers to be correct and for us to be fried. But we made it till Christmas Eve, had a little fun to share with the fourth graders and others. On Pi Day, our message of the day changed, and we ran another multi-node HPL to see if our results were the same. We're continuing to be nominal, as they say. And then recently, we celebrated the year launch of the plan of Spaceborne Computer. And the message of the day is one that not many people will ever get to say. 1 year ago to this minute, I left Earth as the message of the day on a Linux computer. So, after that 1 year launch anniversary, we compared the results with and without our hardening with software. We are running a commercial off the shelf. There is no hardware modifications whatsoever to this to see how they compared. With hardening of software, it's a little bit slower than without in both cases on Earth and in space. We're using about 1/4% of the performance in order to protect the system from itself. It is autonomous self-care. The autonomous part will come in shortly as to why you want to do that. In all cases, space is running a little bit faster than Earth, and I get asked that often. Our Earthbound system is running VPNs and other NASA-required software, and so it does run slightly slower. Here's where the data starts to come in. This is our summary slide of anomalies that we have encountered over the course of the mission. It begins with 8/14 launch. 1 month later, we were powered up, and so you'll see the first little blue bar as a boot. The quantity of events is up the y-axis. We then encountered a power anomaly, which we handled, a network anomaly, which we handled, and as happens, we had an internal power supply failure, but with redundant power supplies, we continued to operate. The next thing you'll see is a level 3 correctable cache error, and then we had our first solid-state disk failure. If you look across the full spectrum, the bar with the tallest indication is a solid-state disk. I've had 9 solid-state disk failures. I have 20 solid-state disks on board. When we designed this, we looked at all those things the experts told us would be affected by radiation, and we ranked them, and we wrote software to work around it. Solid-state disks were not even on the list, but they are failing miserably. Okay. So let me talk about this. This is kind of fun. You'll see a couple of bars up here where there's red indicating a power anomaly followed by a reboot, as you might expect. Just as in your home, elsewhere, smoke detectors have false alarms. When a smoke detector goes off on the International Space Station, they assume it is electrical fire. They cut the juice. There is no warning. Your Linux box goes down hard. And that lasts about a few hours before they can figure out it's not real. And we rebooted successfully after that. Just as we have redundant power supplies, they provide us with redundant inverters. The solar cells generate DC. We need 110 AC, and they have a device called an inverter that provides us with that. One of them failed. We stayed up and continued running. But when they got around to replacing it, they have a safety procedure that says all electricity must be turned off. So that was a scheduled outage. So we did a normal bring down of the Linux system there. Need to the rack power supply. When speaking to astronauts Van de Hey and Resnick, they said the most interesting thing is when a new astronaut comes on board and they try to toss you something. And we tend to have an upward arch. And with that upward arch, whatever they toss you, a sandwich or a pencil, ends up hitting the overhead. We're installed in the overhead. And also, when they begin to move and they push off with an arch, and they all end up with scratches and bumps and bruises on their heads. He was unloading a different Dragon spacecraft, and his knee went up and hit the remote power switch and turned us off. That was an easy repair again, but a second unscheduled outage. The third one is that same smoke detector went off again. We suspected it was false. It would not reset. So it took about 8 days for them to figure out this rack interface controller had failed and it needed to be replaced. So that's why you see the thickness of that bar. But again, we've rebooted. So we've had several unscheduled interrupts, several scheduled interrupts, and we continue to function just fine. I'm often asked, so how is it when you SSH into this? Is it instantaneous? Is everything all nice and dandy? Here's the ping response. We typically get 700-ish milliseconds is the response. Type a letter, get it back like using a modem in the 80s. Okay? That's the way it is. All right, now one of the unexpected things that we've had to deal with in real time is called a loss of signal. Me and everyone else thinks that, well, you're just 250 miles above the Earth, you're going around the Earth, we've got lots of satellites, that you're in constant contact. That is not the case. We encounter LOSs often, and this is a standard output from the NASA-provided software. Taking a look up here at just past midnight, we encountered an LOS at 40 seconds after 11 minutes, and it lasted about 25 seconds. Okay? Well, on a good day, you'll have 8 LOSs an hour, and this was a good day. I had about 8 LOSs an hour. If you haven't written software in a while, and you assume those functions will properly respond when there is no response, you need to take another look at your software. It's not like the data center networking that we have today. When you have a bad day, things can get worse. Here I've taken it from that eye chart and put it up here so that we can take a look over a 5-hour period. Here are the hours, 1500 to 2000, indicating we have an LOS. And this was the longest duration of the LOS during that hour. So there will be times when you are out of contact with your computer for as much as 16 minutes, 10 minutes. There can often be 20 and 30-minute LOS. So our software's had to be redesigned a little bit on the fly to take advantage of that. What do we plan to do if there is a Spaceborne 2? Number one, we're going to take all the components back to Earth. Whether they failed or not, we're going to submit them through our product failure analysis and see what they come back with, and ask all of those evaluators to give us an estimate of the age of this component. Number two, we're going to have to address storage. Solid-state disks are not functioning as advertised. We've got a few ideas of how that could be and whether we should use different ones or consider some other options. I just kind of covered some software design that must be taken in light of an LOS frequency. On the positive side, we believe we can increase the core count within the same power envelope that we've been given for the next generation. And we will this time consider making various virtual machines available to the other payloads on board, most of which are connected via 10 gigabit interfaces if they're doing anything with imagery or sensing, et cetera, so they can handle those 4K type capabilities. Okay? My next to last is to close with this. This is a photograph from December of this year of the International Space Station, and there are 5 spacecraft docked at the same time. So our visits to space are increasing exponentially, and we're not going there just to say that we've been there. We're going there to do things. And the people that are going there to do things are going to need something like Spaceborne Computer and not be able to tolerate 1 and 2 core 500 megahertz processors to do that. So having said all that, let me be brave and pull up. Yes, here we go. This is my dashboard. This is real-time data coming down from the International Space Station as you see it. I think I've already shown you the plot area of where the International Space Station is currently located. John Kachuri is so excited we made it to the 1-year anniversary. He continues to use that as an icon. Up in the top, we have our clocks. It is 12:41 in our lab. It is 17:41 on the International Space Station. Okay? The official definition from NASA of the mission elapsed time is the time since you launched. We have exceeded the 1 year, 387 days and 1 hour. Our system uptime is 356 days. So that's taking into consideration the scheduled and unscheduled interrupts. We've been around the world 5,625 times. The important stuff is down here. In this display, I've got 1 row per server. Space 1, Space 2, Earth 1, Earth 2, and currently they're in a paused state. We have several states, running, paused, hung, or idle. They're currently in a paused state for some reason. The autonomous self-care software has noticed something that it's not sure about, so it has gone into a pause state, and we'll check the status of that parameters in 5 minutes. If those have returned to nominal, we will continue to operate. So at the same time, if there's an LOS, that will show up here and tell us how long the LOS has been happening. We're getting real-time data down every 5 seconds. And the thing that we want to emphasize about this mode of operation is that all of the data that is coming down, all of the data that I'm generating is not coming down. We're doing processing at the edge. You're not going to be able to get your data, Mr. Scientist, from Mars. You need to process it there and turn that vast amount of data into a minimal amount of information and send that information down because it's what's important. So the example I use is there's an ongoing lightning study. And the imagery from the ISS of the Earth showing lightning strikes is being sent down to Earth. It's being processed at Earth. It's taking up a tremendous amount of precious bandwidth. If there's an image that has no lightning in it, it is of no value, but it has to be post-processed to figure that out. You should process that stuff at the edge and only alert the scientists something's going on, it's time for you to go to work. So we kind of use that as an example here. All I got back down is 48 bytes of status data telling me that I'm paused. When I'm not paused, it'll tell me what I'm doing, how long I've been going on. I don't know if this is readable, but I will share it with you. The last time we ran HPL, it took 11.60 minutes in space and 11.63 minutes on Earth. The answers are coming out correct on Earth and in space, and the run times are within the variance that we expect. So we continue to do this 7 by 24 for 365. And we've just encountered an LOS. You see that that has popped up right here. Its duration is a few moments. So we've lost signal. That typically happens at the southern extremities and at the northern extremities. Okay. So thank you very much. We have time for 1 or 2 questions. Otherwise, I appreciate your kind attention.
Very interesting. I got a couple of questions. The first one is that if you guys know that basically clocks run slower or faster, basically, the further away you get into space, and actually they slow down from acceleration. Has anybody done what the theoretical calculation is for the different clock speeds? Or
no.
No.
Within the variation that we tolerate on benchmarks in our group of people in HPC, it's below that. It's in the milli or microsecond.
The second question is, you said it was water-cooled?
Correct.
How did you basically package? I mean, the water couldn't have been sitting there in very well and cold, so was that added after the thing was installed? Excellent
question. So unlike here on Earth or in the data centers that you have here on Earth, in space there's no air conditioning. Okay? There's no air, therefore no air conditioning. If I can jump back to the image, I can show you how that's working. You'll see the large solar cells are that generates the electricity aboard the space station. And orthogonal to those are some other things that look very similar to solar cells, but those are in fact radiators. The radiators are here. And there is a closed ammonia loop, and then there is a closed water loop, and the closed water loop is used to create the environment suitable for the humans, keep the air temperature where it needs to be, move the heat from their bodies, etc., out. And with permission, applying with their specs, you can tap into that medium temperature loop, and that's how we cool it through that little rear door water cooler radiator. Very good question. Thank you.
Hey, Mark.
Yes.
So do the astronauts on the space station do anything to it, or is it all done by you down here?
The short answer is it's running autonomously with self-care, and that's its purpose. And in fact, in the mission debriefs, the astronauts did not even recall installing it. It went so easily. And they're asked a list of stock questions. was any light coming out of this particular payload? Did it bother you? And they said, there's no light. And is there any sound coming out of it or vibration that irritates you because you're living in the lab? And again, they said no. So we've been running quietly, autonomously for almost a year now.
I have a question, Mark.
Yes, sir.
I know there's a difference in capabilities between the older hardened systems and our current system. But is there any information on the uptime of comparison of uptime between systems?
Yes, most of that is anecdotal. More than one NASA employee has told us that Spaceborne Computer has more computing capability than the sum of all the systems on board. So that's why they're interested in us continuing. They also continue to be fascinated with my weekly reports of how long we've stayed up. Because if you look at the number of laptops that they have shipped to the International Space Station and divide that by 6, which is typically the crew, they're going through about 1 a month. Now, I don't have any data to support this, but other than the solid-state disk being a weak point. But again, I'm for computations. So I don't have a keyboard, I don't have a monitor, I don't have a touchpad or any of the other things. And this isn't made for consumer use. So the quality of those components is probably less. And if you're up there and you're an astronaut and suddenly the mouse isn't working and you know that there's 30 of them in stowage, you just take that one, put it in the trash, and get you a new one, right? So the mission critical systems, they come in 3s, and they're constantly voting. They've got to have 2 that agree. And so those on the left side of that for navigation, et cetera, are those small 1 and 2 core slower systems. And they run 7 by 24, 365, and they vote every second or so to see what's up. That's how they get their redundancy. So you have triple the weight, triple the cost, and you've got incredible certainty, which you're going to need for flight. But for our research, we need, I believe we need more state-of-the-art that can autonomously perform self-care than we do reliability by multiple systems. Okay.
Any other questions? Mark, thank you.
Thank you.